All right, so a quick video on the second derivative. So the second derivative is typically we use the notation f double prime of t. And so this double prime comes from the fact that we're taking the derivative of the derivative, right? So it's really kind of f prime of t, and then we take the derivative of that. So the definition of the second derivative is really we're taking the limit as h prime of, or as h goes to 0, so the time interval shrinks to 0, of f prime of t plus h minus f prime of t all over h. So you see the difference? That the function that is inside the difference quotient here is f prime and not f. So what does that mean? That means this is the instantaneous rate of change of f prime of t. So another way to think about that is the speed at which the slope of f is changing. Okay, so if we're talking about the slope changing, that means we're talking about the bending, right? Okay, so if we take a look at an example quickly, just kind of highlight the notation and the relationship here. If f of t is just the parabola t squared, a very simple function. So let's map this out here. Got a parabola passing through the origin here. We know that f prime from our previous work is 2t. It's a linear function passing through the origin. All right, here's f prime of t. Here's f of t. We said f double prime is the derivative of f prime. So now you kind of like forget about f for a second, just take the derivative of f prime, and what do we get? The derivative of f prime, well, it's 2t. The derivative of that would be 2. And how does that make sense with our graph? How is the slope of f changing? Or how is the slope of f changing? AKA, what's the rate of change of f prime? Well, the rate of change of f prime is just 2. It's increasing by 2 for every 1 we increase. So it's actually locked in at 2, and it's a constant 2. So here's f double prime. So this describes the rate at which the slope of f, how the slope of f of t is changing, aka bending. Meaning it's bending at a constant rate. And so that's what describes how the parabola is really shaped. Okay, it has this constant bend factor, and this is it. Now, bend factor is not something we talk about formally, but this is one way to view it. Okay, so this is getting cut off up top. But anyway, so that's what the second derivative really is. It's the rate of change of f prime. So I want you to make sure you've got this notation down. And when asked to calculate this using the limit definition, this is what you'd use. I obviously chose a very simple function here to illustrate it, but let's work through a couple examples to highlight the importance of this thing. So here we'll look at the numerical perspective coming from a table. So we've got C is the number of passenger cars, and it's a function of, and this is in millions of passenger cars in the US in the year T. Okay, so for part A, it's asking do f prime and f double prime appear to be positive or negative during the period 1975 to 1990? So we're just looking here. And so for f prime to be positive, what does that mean? It means we need to see that C, the output, is increasing. And so from here to here, we see an increase. We see an increase here. We see an increase here. So what does that tell us? Excuse me there. So what does that tell us? It tells us that from 1975 to 1990, dc dt, aka f prime of t, is positive. And we'll write here, since c is increasing as t increases. All right. Now the question is, how about f double prime? And the notation in Leibniz notation is a little bit weirder. You'll see it's got this like we have with trig functions, the squared operator comes before the variable, and then it's dt squared on the bottom. So I promise you that's not just to be confusing. It does have some relevance. It's just beyond the kind of the scope of this class why that's the case. All right. But d squared c over dt squared aka, you can just use double prime. And so how would we tell this from the table? Well, this is how the slope is changing. Okay, so what we actually want to do is calculate what this change is here between each of these intervals, and then look at what the trend is in the in f prime. All right, so I throw these into my calculator to see what the change is here, and if we can see a trend. So from let me bring my mouse over here. So from 121, or from 106 to 121 here, or rather we go by the input, from 1975 to 1980, what's the change? We see it's an increase of 14.9. We know it's all increases. From 1980 to 1985, it's an increase of 6.3. And from 1985 to 1990, it's an increase of 5.8. So what do we see? Yes, it's increasing, but the rate at which it's increasing is going down. Okay, and so this is that new layer of analysis that we're able to give. It's, yep, something's going up, but the rate at which it's going up is going down. So what does that tell us about the situation, right? So here, what we see is, let me jot down these values onto our notes here. 14.9, 6.3, and 5.8. Okay. So we see that this is actually negative, since f prime of t is decreasing as t increases on this interval. And all of this only really applies 1975 to 1990. Right? We're not really looking at the rest of this right now. Okay, so for part B, I'd actually like you guys to do that on your own. Does it appear to be positive or negative during 1990 to 2000? So you should be able to kind of frame what you're doing there with what we just did. For part C, we're looking to estimate f prime of 2005. Using units, interpret your answers. So what we want to do is take a look at the net change here. All right, and we see that this should be, what, just 3. So it goes up by a net change of 3. And the units of this will be, dc dt. Another way to represent this notation, this is Leibniz notation with the evaluation bar. Oh, you guys can't see that. I'll give you a second to catch up here. So estimating this here. dc dt, this evaluation bar says at this point. It means the same thing as this. Okay, these are the same. And so what we see is that there was a change of 3. And we'll put approximation signs here. This is not equal. 3 over 5. So 3 million passenger cars over 5 years. Okay, and this is kind of really the best guess we've got for what's going on here. You might be able to get a little bit more sophisticated, potentially even using the second derivative here, but we're not going to get into that here. So 3 million cars per 5 years. So if we're trying to estimate what's happening at that point per year, we want to drive this to a unit rate. So we'd simplify 3 over 5 to be what? 0.6 million passenger cars per 1 year. And so what does this really mean? Well, this means we estimate that the number of passenger cars in the US increased by 600,000 at the start of 2005. So let me box this in. The number of passenger cars in the US increased by 600,000 at the start of 2005. Okay, that tells us the rate of change. It tells us the moment in time we're talking about, and it has the units included there, as well as how it's changing, right? It increased, not just using that language of change. Okay. So let's pause there for a second and do one more example. Here we'll be looking at the graphical perspective of the second derivative alongside the first derivative. So how can we map the notation to the graph? Excuse me. So here, first of all, this is written as, it's f of t in the graph. Let's just go ahead and change this out for x so that we don't get super confused. It's all the same, but let's make sure we're all on the same page. So where is f of x less than 0? Well, let's not overthink it here. This is where the graph dips beneath the x-axis, right? So that is from here to here, right? And then it doesn't come back through again. So, you know, we could maybe highlight this with the blue. If you'd like to, you know, label points between A and B, something like that, whatever works for you in your notes. And now it's asking, where is f prime less than 0? So f prime being less than 0 means what? This implies that f is decreasing. Right? F is decreasing. So that would be where? Well, that happens here. And that also, and then f is increasing up until this point where it turns around, and then f is decreasing again over here. So we could use this red line to indicate that. And so these are interchangeable, right? Here and here, these are the same sets of intervals. And then it's asking, where is f prime decreasing? So again, f prime is the slope. And so this is really asking about the second derivative. Oops. This is really asking about the second derivative. So if f prime is decreasing, that means the slope of tangent line is decreasing, which means that f is bending downwards. We call this concave. And the new lingo is to call it concave down. And so you can really think of this as, you know, what does a cave look like? If you sketch a cave, it looks like this, right? This part here. It's bending downward because think about what's happening as we go from left to right. The slope of the tangent line is going from positive to negative, right? Pretty steep, getting less steep. It's 0. Now it's negative. Now it's even more negative, right? Etc. So that's what we mean by concave or bending down, or that f prime is decreasing. So where is this happening on the graph? Well, that's happening here, right? Between this point here and this point here, the function is concave down. So, you know, again, you could use labels here maybe because we've got so many different things going on. Between A to B, concave down means that that f prime is decreasing. And now this fourth piece is asking, where is the slope of f of x positive? All right, so the slope of f of x being positive means that this is where the function is increasing, right? Where is the function increasing? The slope is positive. Will that be like here to here? And that's pretty much it, right? Since it's decreasing everywhere else, this is the only place where the slope is positive. And then it's asking, where is the slope of f of x increasing? Now that's, again, I see this instantly, but so I need to pause. What does that mean, the slope of f of x is increasing? That's the same as this question here. F prime describes the slope of the tangent line, or the slope of f. So where is the slope increasing? Well, now it's not where it's concave down. It must be where it's, aka, bending up, since it's increasing. So instead of concave, we call that convex, which means something like this. Because if you take a look at the slope of a curve like this, from left to right, it goes from decreasing, very steeply negative, to less negative, to 0, to slightly positive, to very positive. So the slope is going from negative to positive, which is increasing, right? Just like in our bank account or whatever, or from temperature, going from negative to positive is increasing. So it's bending up. And so where is that happening? Well, it's bending up from here to here. Let's do this graphic's a little bit busier than I anticipated, but that's okay. You know, from dot to dot here. That's where it's concave up. Okay, so that's all I wanted to cover with this video is, again, this graphical perspective on how a function bends or its concavity, whether it's concave or convex, how that relates to the sign of the first and second derivatives, the definition of the second derivative, the fact that it is just the derivative of the first derivative. Again, saying it like that doesn't really help that much, but in terms of just defining it, it does. And so this brief example of how the second derivative operates, it tells us how it bends, and then how we can see that in numerical examples, keeping track of units, and navigating that whole setup there. So I hope you found this helpful, and we will see you in the next video.